Any questions to that, or union is clear? Okay, we can choose something another, like intersect. Basically, intersect is, as explanation goes here. You have the input, you have the intersect feature, and you only get the intersected feature. So the result that you have is only the intersect between both features. If there is an intersect, that's all you're going to get. We can actually try it in the original land use feature classes, because some of them overlaps together, because there's some problems with this data. So we can choose, for example, this, and we can choose land use. We're going to check what the intersect is, where is it, and we make a run. Yeah, and as you can see, all those, we have 227 records here. So it's 227 features that basically has intersections between them. And of course, I can check the attribute table to check what are the specific data from them, from both of the different features. So we have some data on the district, we have some data on the land use, and we can compare that and check why it was placed in both. You can actually check, because I was trying to check others and land use. Of course, this others should have been just the something that didn't contain, was not contained in the land use from the start, but for some reason it is contained in it. Some those 227 are contained in it, and we can consider that some form of a discrepancy in our data. Whoever created the original data made a mistake. We should have more validation rules so that they don't repeat data. That will give us an option, for example, to use another tool from the overlay. It's rather new, remove overlap, which basically gives us the idea to check if there is overlap between two different features, and create one that doesn't have the overlaps. Only the unique features will be added. So this is the overlay. This is the proximity. We can check quickly the clip function. Basically, as we said before, clipping is just, I'm going to use a feature to clip my data. So what data I'm going to use? For example, here we're going to use the land use. I'm going to clip it using the districts, but before that, we can open the districts. So this is the city districts, and I'm going to make a selection for those two districts. So I'm choosing those two districts, and then using that as my clip feature. And since I'm already made the selection, what will happen now is I will only get the land use inside that selection. And then I run that. And as you see, this is what I get. Only the land use inside the selection. We can check. This is the original land use. And this is the one we have now because we made that clip function. Okay, are you with me so far?
Yes.
Yes.
Okay, we are going to try moving into something more more complex. Well, usually special analyst tools are more complex. So let's start by turning some of our data into raster. No. Then okay, as you see, I was looking for a function and I can't recall where it was. I know it's in a special tool, but analyst toolbar, so I just wrote distance. It's basically Euclidean distance. This is a tool that calculates distance in a Euclidean fashion. So just click on it. Okay. So this is the tool, this is basic tool, and they also get you the message that there is a newer one, which is called distance accumulation that you can switch to. It's the same function. So I can also go to that. Okay, so we're going to calculate distance. This is a short explanation for what distance does. Most of the tools, you get some form of a graphical representation so that you can understand it better, but not all. You probably get some graphical representation inside the help. If you check the help, maybe you can get more. But anyway, we are going to calculate the distance from land use. And then this is the barrier, and this is no, we don't have to have a barrier. Okay. To the axis. So basically the calculation will be done between the land use and the axis, how their distance looks like. We could have a surface raster that basically have the Z value, the elevation. We could have something called a coast raster, which is basically defines that moving across the field has some form of cost. It takes time, it takes effort, something like that. So we get not an arbitrary number, but we assign a cost to how much it costs us to move from one point to the next. Sometimes you get something like that when you're running an analysis, like a distance accumulation. Sometimes we also have a raster for the direction, but let's say we have only those are the basics. We don't have to fill the rest. Okay, we can close what we don't need. Where's the access? Okay. As you see, this is the raster that we get. It was stored here. It's called distance length. Okay. This is the raster that we get. It's based on the extent of our map. And if we zoom in, as you see, this is the stretch that it was. It's between 0 and 18,028. So basically 0 and 18 kilometers. Some places, of course, gets that 18 kilometers. We can check the value because I forgot some parameters to enter, which are important. So for example, this is the property. It tells us the basic data on this raster that we just created. And this is the raster information. See how many columns and how many rows, and this is the raster resolution. The raster resolution we have here is 119.45 meters. Of course, this is a huge cell size. We might prefer something smaller so that we can work with it. We can check the symbology for that. Symbology for raster is a bit different. So this is a stretch based on percentile. Now I can do something else. You can make it classify. And add classes. This is a way of symbology, running symbology for raster. Okay, so this is the raster data we have right now. When I said that it's going to be classified based on 10 classes, this is the 10 classes that we get. And the first class is from basically 0 to 900. And then the next is to 200 and so on. You see, most of the data is here, but because the cell size is very big, the cell size that I forgot to add to the data is very big. The stretch is huge, so we can make the data more complete by going into the environments and define the cell size here. No, that's raster storage. Yeah, cell size is maximum in inputs, but we can choose something different. So we can make it something like 25. Okay, and make a new raster, run it. Okay, so this is the new raster that we have. And we can check the symbology for that one as well. Make it the same as this. Okay, so classify. turn that into 10 classes as well. Okay. And you can check if we check between the differences between both of them. It's a bit different. I think we can go to histogram. If we check the histogram, if you want to check how your data looks like, this is how the data looks like. So from 0 until 815, they consider that one data, but there is also a number of values. So I can actually cut those values as much I want. Classification of data is done on statistical basis usually, unless we do it manually. And this is the statistical method that is used. It's called the natural breaks Jenks, and it has some. If you click here, you get some explanation. We can do it manually if we want. Some people would prefer some form of a manual explanation for some reason or another. But if you don't want to do that, we use one of the already defined techniques. So this is how it looks if I do it as quantile. If it's equal intervals. Defined intervals is not something like manual. We have to enter something. If it's geometric level, this is the geometric level. And based on standard deviation, this is how it looks. And yeah.
Dino was asking, can we get a small project file as an example to make a practice on it after the course?
Well, there will be. I'm going to send you a training for spatial analysis. So there will be training for spatial analysis. You can work with it and you can manipulate the data how you like. You can use it for different things. You can do the exercise and then use the data for whatever you like. Okay. Okay, as I was saying, there's standard deviation. Standard deviation, of course, would ask you if it's first standard deviation, second standard deviation, and so on. So you can choose from that, and it works by how it checks the data. Okay, symbology to raster data is a bit different from the symbology for vector data because basically we have cells that has numerical values, and so you get more tools that has to do with manipulating such numerical values. So this is what we get when we do classify. We have stretch, we have discrete, we have unique values, although it wouldn't work in something like that usually. And vector fields, although we don't use that here, we use it in other things because it denotes direction. So this is not where it could be used, right? But basically, this is how it looks like, and we basically have this as a raster data. So we have now raster data that we can work with. So we can go back here. We can run Euclidean distance or distance accumulation to different fields as much as we like. Here's distance accumulation that we were using. Yeah, okay, we can also run something of neighborhoods. Don't have points. Maybe on focal statistics. But it also one cluster. Okay, just a second. Find something more suited for our use. Mhm. And then we have to use one of those. We can do that. Okay, we're going to run zonal statistics, but we're going to run it to the distance that we already created, the distance accumulation raster that we already created. Do you understand what the distance accumulation raster means? First, before we continue, do you understand what it means? Guys, are you with me? Hello.
I'm not sure what can you repeat the question?
Do you understand what this raster that we created, this raster on the background, means?
I think I do, but I don't know if I understand the question, what it means.
Okay.
In which way?
This raster basically calculated the distance between the roads and between the roads, the access roads, and the land uses surrounding it. Okay, so basically it calculated the nearest distance between any part of the land use and the access we have, and basically created this raster for us. If we clicked on any point on that raster, basically we're clicking on a cell, and what we'll get it is the data on that cell on the raster. So we can, no, sorry, we can close that so that we don't have that. So you see, it calls us classified pixel value. So this is actually the pixel value here is 425. Here it's 2000. Here it's 25. Here it's 0. So the pixels here are very close to the road, so they get a 0, whereas those also are 0. Okay, this is a 35. This is 74. So basically, we are measuring the distance. What this is doing is measuring the distance from the axis outward. Okay, so from the axis outward, we are measuring the distance of every cell we have. Okay.
Yes, thank you.
Okay, so this is what this function did for us. We basically measure the distance from any one feature to the next. Okay, zonal statistics just run statistical analysis based on the data on the zone. So I'm going to use the same districts because they form the zones. Okay, and I'm going to use that raster against it. I'm going to run the zones based on the district. Okay, so basically I'm adding the district. And what are the zone field? Usually the zone statistics run on a zone. So what would be the zone field? I use the districts themselves. So each district here. So this is the district data. So those are the districts of the city. And basically, when we run the statistical analysis, it would be run for each zone of those on its own. So for each zone of this, the statistics will be run and give us the results. So it's done for that, and this is its name. And what type of statistics do we want? So basically, are we going to ask for the average or the maximum or the median, minimum, percentile, range, standard deviation, or sum? We leaving at the average and run it. Okay. So now we have a new raster. Okay, so this black and white thing is the new raster that we get. And basically what it did is calculated the mean of each of those zones, which is the district. It basically calculated a value for me, and we can check that value now. So this is the mean value inside of this raster. So since this is calculating the distance of the roads, the distance from the roads, you can say that there is a road here within 100 meters from in this district. There's a road within 105 meters in average. In that district, we have 200 meters. Maybe in that district, we have 56 meters. On another district, the ones that get the whites, there is a road in average every 3.5 kilometers. This one, we have a road in an average every 267 or 76 kilometers. So basically, it ran the statistics on how many, on the averages of the roads that we have. Does that make sense? Can you understand it?
Yes.
Okay, we can do something, try to do something more meaningful. So maybe run a focal statistics. Yeah, I think. No, but focal statistics, right? No, I want something that starts from. We can, yeah, we can. So we're going to run now something like this. The same process that we just did with the zonal statistics. We're going to repeat it, but start to try to make something more meaningful. So let's think of it like this. This is the land use that we have. Okay. So this is the city land use. And we're going to try to calculate for each district in the city. The districts are the one in red. We are going to calculate for each district the average of the building density inside of each zone or inside of each district. Okay. Do you have suggestions? How do we do that? Any suggestions? Anyone?
You can say anything, even if it's wrong. You're just learning something new.
Let me repeat it again. For each district in the city, we are going to calculate the building density within it. Okay, so we're going to calculate the building density within it. Right now, we have that data in vector format. So each district has the land use inside of it, and those are basically the buildings. And we're going to calculate from that the building density inside each district. And of course, that building density, that whatever the output we're going to create, the output will be in a raster format. So how do we go about doing that?
You rasterize the data.
Rasterize what?
The vectors.
Yes, the first thing is to rasterize the vectors. So we're going to go up here, and we're going to go to data management. And what happened? Okay, this is data management, and in data management, you have to find raster. No, I'm not sure. So there is a function called to convert raster to polygon. So it's Polygon to raster. I know the name. I just know. Oh, sorry. Polygon to raster is in conversion tools. Sorry, I got to data management by mistake, but it's in conversion tools. There is the function that is polygon to raster. We click here. So this is the conversion tools, and we have to raster, and we have feature to raster, multi-batch to raster, point to raster, polygon to raster, polyline to raster. And of course, we are going to choose polygon to raster since the data we have is polygons. We're going to choose land use. Basically, he's asking if we're going to give values, a value field, since we're going to make a raster. If you check here, the raster that we created, if we right click on it, we don't have an attribute table. And this is also a peculiarity of raster data. Usually you don't get attribute tables with raster. We can create ones, but it's forced. Usually we don't have. And why don't we have? Because basically it has a pixel value and that's it. Each cell has its own pixel value and that's it. So we don't have an attribute table. It's too much of a hassle. You have the raster data and you can click on any of the pixels or any of the cells. We don't say pixels, we click on any of the cells and you get the value of that cell. So basically when he asks you for the value field here, he's asking which of the fields does he use as the value field for the raster. We can create one specifically if we want. If we don't, we can choose any one of those. So for example, if I wanted to show the land use, I have one here for the land use. If I wanted to show the land use, I would choose that. Of course, I have a problem with the land use here because it's written text. It's not coded. It's not 1, 2, 3 and have a code in a domain or in somewhere, but it's actually written text. So I'm not going to use it, but the correct way is actually having the land use in coded format, and I would simply choose it. And whatever the system creates, every pixel will get be calculated based on the will get a value based on its actual land use. Okay, so I will leave it at object ID now so that we don't go into that hassle. It will create one for us. Land use polygon raster. It will do the cell in here, and this is the cell size that it's creating for us. Its suggestion that the cell size would be 98 meters with big for my taste, so I'm going to make it 25 as well. 25, no, sorry, 15. Considering the parcels in the city, some of them are smaller, so we just make it 15, and then we're going to run this. So we can turn that off. And as you see, this is the raster that we created for the city. So this is the different rasters. And basically it calculates each cell, gets a value based on what the feature class it represented was made of. If you check, this is how it looked before. So if we zoom in on any of those polygons, this is the original polygon. And if we turn it off, this is what we get after rasterization. So this is what we get after rasterization. So each polygon that we had before is now simply a collection of pixels. For example, something like this was actually that. So you can see this L-shaped building When it was rasterized, it basically became those 4 pixels. And that's because I made it 15 by 15. Each pixel here is 15 by 15 meters. If it was bigger, maybe some of that building might not show up at all. As you can see, that building didn't actually rasterize. This one, this guy, it didn't rasterize because the size of the pixels was too big. If I made it 5 by 5 or something like that, this one will show. So you have to take care when you're rasterizing that you taking a level of rasterizing simplifies the data, and the simplification should have a limit to it. Someone had a question, I think. No questions?
No.
Okay, so we have rasterized this. So this is the data now. So since we rasterized the data, we can still go into zonal statistics. We'll still choose the district as the zonal function for us, as the zonal data. It's asked for the zonal data, and then we're going to choose the city itself, the polygons of the city itself, as the input for the value raster. And we are going to also calculate the mean value and then run. Okay, and this is the raster that was calculated for us. So basically, if you see here, you get such values. So this is 3,244.3. So this is the mean value in this district. You can have the districts appear for us for a second. So we can check each of those and check how the mean values look like in them. Of course, the values that we get here are not wholly accurate, because the mean statistics here actually run on calculating how many cells are inside each of those. So if I want to calculate that right, I might go into another process where I actually make use of the raster calculator. As I said before, you understand the raster calculator is a simple calculator. You have operators, plus, minus, equals, more than. We have conditional operators. We have mathematical operators like the exponential or the logarithms or power or rundown and so on. So we have all the functions, and what we do is we usually run that into a calculation. So what we had before, if we check the data before what we got, this is what we get. See that we have pixel value, you have an object ID, and you have a count. The pixel value is basically 800, basically 84, and there are 119,709 from it. So from this value alone, the one that gets pixel value 84, there is 119. So it basically responds to this or corresponds to that building. or whatever is here in the city. If I zoom in and I choose that, this has a pixel value of 6916, and there are 279 from it. The one beside it has a different value, and there is 37. So basically, this is the number of pixels in each of those. So I have here 37 pixels. I have here 30 pixels. I have that 29 pixels. As you can see, there are difference in color when we zoom in. They're not the same thing. Okay. Each pixel of those is a 15 by 15 meters. Okay. Each pixel of those is 15 by 15 meters. And if I want to know the total area of one of those, I'd have to basically, if I say this is 30 pixels, the total area is basically 30 multiplied by 15 square, right?
Yes.
Yeah, no, is that clear? So it knows
Yeah.
that this is how it should be calculated. It is 30 multiplied by the 15 square. This is how this should be. So this would be the area of this zone and or this building, and this would be the area. If I check the area of that building, it would be the same. It would be 37 multiplied by 15 square, and so on. So each one of those will give me the area. What we need to do now is basically run a calculation so that each set of pixels here gets a unified value. And then from that unified value, we can run we can rerun the zonal statistics, because the one we ran before, the one we have here, the value that it gets is a bit undecipherable. If we want to say that, if we want to decipher that, we can decipher it fully. So we have to reshuffle the data. That's something that happens when we work with raster data. Sometimes we have to manipulate the data on several levels until we reach the one we want. So we have to go to I'm basically calculating how to do that with you right now. So give me a couple of minutes, checking which tool is better. Work. You could have suggestions if you like. I'm still solving it.
Sorry, I have a question.
Yeah.
You convert polygon to raster. Can
Yes.
we convert features to raster or not?
It's the same thing.
Feature, can we convert?
Feature to raster, polygon to raster, line to raster, point to raster. It's the same thing.
Okay. Okay.
Feature is just generalized. Feature to raster is just generalized. But we can choose point to raster, line to raster, polygon to raster. It's just calculated, and that's it.
I think about population and height of buildings or other. That's feature.
Yes, we can do that as well.
Okay. Okay.
Because when we do anything to raster, so when you do anything to raster, polygon to raster, like we chose, for example, it always asks you what the value field will be. So when we add something, I'm going to choose, like we choose here, the land use. They ask you what is the value field. So we have to check what will be the value field that I'm going to add. So it's something that we can add here. I left it here as object ID.
Okay.
We can have it as name, type, land use, and so on. So we have different values that we can place here and then run our calculation based on it.
Oh, okay. It depends about the data that we add.
It's what?
Depended about the data that we add to the
Yes,
map.
it depends about the data that we have already. So it depends
Okay.
about the data that we have already, and we can actually have some form of customization to that data if we wish for.
Yes. Okay.
So sometimes we have customization to the data itself, so we can customize the data if we wish for, and it just turns. Yes, and I think I know where the missing link is. I've converted this to raster, and now each pixel is basically 15 by 15 meters, 15 meters square. And I'm trying to run zona statistics based on it directly, which would make a problem. So we can actually separate all the pixels again, which goes to point. There is a tool here called raster to point. It's the reverse of what we're going to do. So we double click on it. I choose the raster that I created. We're going to turn each raster into a point based on value. Let's see, make sure it's right. This will take some time. So I think this one will take a couple of minutes. But it's basically what happens when you do with raster data. It takes some time to run the functions. So now we are done, and check that we are done. Yes. So as you see here, what happened is that each pixel that each cell that we have turned into a point. So there is points here that we can make a bit bigger to check it. So each one of those is now a point. Okay, each one of those is now a point, and that covers the entire map. Okay, and we can move from that. Basically, if we can calculate each point multiplied by the area that it represents, because each point now represents this 15 square meters. Each point now represents the 15 square meters and minimum distance. Is Mohammed, do you have a suggestion?
Sorry, but why we need to convert raster to point?
Why do we need to convert raster to point?
Yes.
Because the raster that we created earlier, the values in it were values that were given to it's the object ID. It's basically the object ID, and when we try to run a calculation, basically the calculation is run on the cell value, and this is the cell value that they find. So if I try to run the calculation, it will check on the cell value, and the cell value is basically the object ID. And so any calculation I'm going to run, if I say, for example, let's multiply by 15 square, It will basically multiply the number of cells.
Okay, yes.
It will multiply the value of that cell, which is an arbitrary number, and so it will give you bad calculations. Okay, so it gives you a bad calculation. So I'm trying to unify that and make it no, it's not based on that. It's based on the number of the cells. Okay. There are many ways to do it. We will trying, and maybe I'm making it more complicated. And this is part of using spatial analyst, is that there are too many functions, and we're trying to figure out how to do it exactly. And usually what we do is we draft down the workflow. So I'm going to do that process, and then I'm going to do that process, and then I'm going to do that process. I'm trying to do that now on the fly with you. I haven't tried that before, so I'm doing it on the fly with you. And I'm just trying to think of the better ways to run this or run that or run that. And sometimes it takes some time, but the discussion is important. That's why I'm trying to engage with discussion with you, because sometimes we just can figure out certain solutions. And I just thought of a solution that might be much easier than turning into points. Let's do that again. Let's do, yes, then linear raster. This is based on value. It doesn't matter if I make all values equal 1. Yeah, it might work. This might work. So reclassify is a tool that basically allows us to change the value of the raster. So whatever raster that we have here, as I said, the value that it gets from the object ID, and it's an arbitrary figure. It doesn't help us when we're trying to run the area, when I'm trying to run the area. But anyway, what I want to do now is basically multiply everything that I have with 15 square, and based on this multiplication, then we make the zonal statistics. So the classify might be where we actually work. We can actually say that we're going to just a second. So this, and why take the count? Shouldn't have. Just again. That, yes, and okay, so value, we're going to classify. So the system here is going to do is basically tell me I'm going to classify. Those are the values of the cells that we have, or based on 5 categories, and I can say okay. So those are the values. It starts as, ends as, and these are the new values. If you check here, the new values are automatically set at 1, 2, 3, 4, 5. But basically, I can make them all 1. Basically, what I'm doing here is making sure that each of the cells that we'll have, each of the cells of the raster that we're going to produce now, only have a value of 1. So when I go to the calculator and choose that and select that one and make it a different figure, sorry, multiplied by 15 square, I will just get the value of that directly. So now we're creating the new raster, reclassifying and getting a new raster. So this is the new raster, and let's keep that and that off, and we check it. You see the value is 1. Everything has a value of 1. So this makes it easier for us.
A value of point?
Each cell now has a value of 1.
Okay.
So each point now has a value of 1.
Before than 15?
Before it was, now we're going to multiply by 15, so we can go to map algebra again. And in map algebra, I have the raster calculator, and I can simply say, I'm going to take the reclassified lands and multiply that by 15. Squared. So this is the icon for the squaring. Okay, so I'm multiplying this by 15 squared. Run it. So now this is the new raster. If I click on any one of them. Okay, something went wrong here because it actually gives us a value of 0 when it should have been much different. So let's do it another way. Times 15. Okay, so now it's correct. So each cell is now calculated as 225, which is 15 by 15. So now it's working. Okay.
Okay.
And we go back to the same thing, which is the zonal statistics that we started from. And this time I'm saying that the zonal statistics will work on this reclass. It's called reclass raster. So it's, sorry, this is the zonal data. So the zonal data is here. And the field is going to use is the district. And we're going to use reclass raster. And that's it. And we're calculating the mean and run it. So now it's run over the entire city. And we didn't make a selection, right? We didn't make a selection. For some reason, it seems like it's calculated not the mean, but something else. Oh yeah, it didn't aggregate. Okay. It's 225. We have to calculate the average inside the zone. Oh yeah, so this is how we have to normalize the data. Basically, each cell, this is why we got another phony result. I'll check how to fix that and come back to you. But basically what happened here, because each cell is 225 and we're asking for zonal statistics and calculating the mean. The mean in every location is 225. It's the average of the results. We have to combine all the results together and then run the zonal statistics. So we need an extra step. I will think about it in the rest, give you some rest now, think about it and tell you how to do it. But before we go to the rest, I will just show you something that is very important to what we were doing right now. Did you notice what I pressed on? This something here called the model builder.
No, I
Yes.
don't have.
Yes,
No,
I
no.
pressed on the model builder here on the analysis. We have something called model builder. Okay, I pressed on the model builder and it opened this window for me. So I have this window and it have its own ribbon. And why do we use the model builder? Because some of the operations that we do on spatial statistics or on any spatial analysis, whether it's raster or vector, might require us to move through a number of procedures, one after the other. And as you see now, I was trying to do it, and then I have a problem, and I'm not sure is this one would work or this one would work. Usually, as I said, we draft it down, so we might get a piece of paper and just draft down how to do those processes, how to walk through them, and after we are finished, we have to try it. But even we draft the thing, we might miss something here or there, and the results will be wrong, and repeating everything that we've done will take a lot of time. So moving with the model builder would be easier. What is the model builder? Model builder is basically a form of graphical representation for our work. So what was the first thing we did? We actually turned our polygon into raster. So what I did here now is I got here to polygon to raster, and I basically dragged it into this model builder. So I have it here, and I'm going to enter the value for that, saying that this will be run by the land use. This is how it's run. We said it's 15 meters. So I basically enter the parameters for that. And this is what we get. So this is the first function. So I have land use. I'm going to turn it from, this is the function that I'm using, the process, polygon to raster. And this is the output I'm going to get. After turning into raster, we want to do the reclassify, for example. So here is the reclassify. I'm going to also drag that here. And basically, I'm going to make a connection between that to that, making that this is the input from one to the other. No, not new model. Sorry, not like this. Activities. Input, so I'm connecting that to that. Okay, so I'm connecting that to that. I'm saying this is the input. So this, whatever I'm creating here will be the input to that. I still have to enter some parameters for this, how it works. But basically I'm saying this will give that. And then after that, I'm going to, what we did was going to map algebra. So here's raster calculator. And so the input from this will go here. And we'll enter some expression. I haven't entered the calculation yet, but we'll check what the calculation would be. And then I'm going to go into zonal statistics. And I'm going to take the results from there, edit, enter it here. So this will be the input value raster. And because I'm going to enter something extra from here, I can actually drag this feature directly and connect it here and say this is the zonal feature. Okay, and once I did that, I can just say auto layout. So I'm just clicked here on auto layout just to see how it looks like. So basically, this is the function. The ones that you see having color, not grayed out like this, means that the parameters for running is already online. Those still miss some parameters, so I can just click on them and check what is missing. So This, for example, still needs the equation, so I can enter the equation. This one still needs, of course, once I enter the equation, the output here will also have a color, and I can also choose some options. And once I'm done with that, I can simply say, run the model. So I can click here for running the model and check the results. So I would see the model is running, and whatever output comes here will be added directly to my content, and I can check the results. Is this the correct thing, or is this wrong? And if it's wrong, I would see how I should edit my model. So basically, it makes for going back and forth and adding different functions or trying different functions to reach for the solution. I already have my solution neatly presented graphically, and what I'm going to do is go back and forth through the different functions, maybe replace one of the processes with another one, add a different process or an extra process, and finalize the entire thing at the end. Okay, so basically take it through. This would help me take it through the iteration. And of course, when I'm done, I can save it and share it with my group. And if I want, if I have much more complicated ones, I can actually save that into a Python code and give it to my colleagues, or share it as a script that we can actually load in the toolbox and have it to be used regularly if we wish. Okay, I think we can take a break now and come back to finalize the next session. I will check the solution for this one and come back to you after the break. So this will be the 1 hour break.
Okay, thank you, Monem, for that. So before the break, do you have any questions?
No,
Okay,
thank you.
so then we can come back in an hour. Yeah, thank you so much. Maybe they will just see the recording afterwards if they miss anything.
Okay. So before we move on about how to solve the issue of calculating the building density inside the different districts, I already found a solution, and it's much simpler solution that what I was doing, and maybe I was a bit fixated on solving it through the spatial analyst, but there was much simpler solution. So what I did, I will just go through the steps before just simply. So what I did first is going to the dissolve tool. If you recall, in the presentation, we talked about it briefly, how it aggregates different tools together, aggregates or simplify the data we have. So I started with dissolve, and what I dissolved is basically the land use itself. The land use has in its table, in its attribute table, it has a field for the districts of the city. So it has a field where each piece of land, each parcel that we have is already attributed to a district. So I ran the dissolve and created a new feature class, and this was its layer. So if we check it now, once we dissolved that together, what we get is a new feature class with only the districts and the aggregate areas of all the land parcels inside of it, the land use parcels inside of it. So basically here we have the areas for all the land use parcels inside of it, and here we have the district names. Once I have that, I basically have the aggregate. All I have to do now is somehow get the areas of the different districts, the area of the district boundary, to be added here, and somehow make the calculation so that I can basically get the density. So it's between the area of the aggregate area that we have here divided by the area of the entire district or neighborhood, and like that we'll have the density or the urban density. So what we did, or what I did, is I actually used spatial join. So I made a spatial join between the districts and the dissolved land use, and got a new feature class, which basically combined the data of both of them. And now here I have the original aggregate area of all the parcels and the area of the district as a whole. And then I added a new field called the density, and simply made a calculation. If you click on the field, you have a calculate field, and in calculate field I simply made it like this area divided by that area. I think the calculation is already there, so you can just check it. So I just made it this area divided by this area, and apply, and the calculation is done. And as you see, just the area is already calculated for the entire city. So each district had its own urban density, and that's it. So it's a much simpler and much quicker solution to what I was trying to do using the spatial analyst tools and so on. But that's normal. It's not uncommon. Just to give an example, when I was working with my PhD thesis, I had to plan a big model for part of my calculations, and the first model I had to build it in Model Builder because it was considerably large. So I started from scratch in Model Builder, and the first run for this model, after fine-tuning all the bugs and the errors that came out, took 24 hours. So 24 hours to run without any errors, just to run from start to finish and give me some results. It was 24 hours. I think it took me 3 weeks to simplify the model, and the simplification made it run into something like 8 hours. And the next iteration for the model take me something like 3 months. Now it ran at 2.5 hours. I think before I started writing my thesis itself, started writing the practical part and the conclusions and so on, I had the model running at 45 minutes. I had to run that model a couple of 100 times. So you can imagine, it's not just I have to run the model once. No, I had to run the same model in several iterations with different data for a couple of 100 times. So running it for all the optimization that I can get and make it more simplified, more quicker in its running, the optimization is very welcome. So any minute that you can shave off the model would be better. So when I reached that 45 minutes, that was very exemplary. I mean, 45 minutes took me 3 months to finish running all the iterations of the model. So you can just imagine if it was much longer, how much it would take. So running with such models will take you some time, but designing it, it's what we do. We design the analysis itself. We sit down, we draft the workflow of the analysis, and the model builder is one of the most important tools because we start drafting the analysis one process after the other. We can run parts of the model. We don't have to run the entire thing. I can just click on part of the model, right click on it, and just run. So it will run whatever is before that until this step. We can check how it's going on, so move on to the next step, and so on until we have something more viable and something that we can work with. So that's it for here, and we'll return to or move on to the next topic.
So just before we move to the next topic, was it clear what Monem did in how to calculate the density for you, or you have questions?
Hello.
Yes.
I want to ask about how much time do you need to complete this project? As we see, you share your project. How much time did you need to complete it?
Which project?
That you present?
The one the one that we had on the screen?
Yes.
No, that's data from a project I was working on. So it's
Yes,
it's
yes.
not...
I mean, as you work in this program, how time you need to finish a program like that?
Finish what? Building the database?
Yes.
Building the database for that project, I think took I think 3 months. But we already had the data from many sources. We were just compiling the data, editing the data, doing some aggregation, and then studying how we're going to run the different analysis that this specific project required. So just doing the edit work maybe took 3 months, and maybe another 3 or 4 months to do the different analysis that was required from the client and so on.
Yes, I think it's more than a year or 2 years, I think, like this.
No, it doesn't take that much. It depends on the project, but it depends what you were doing on the project. This project didn't require some of the most hard, so let's say, analysis that is required.
Yes.
It was more, I wouldn't say it was 100% straightforward, but we had a clear goal from the start, and we knew what type of analysis that we had to do, and so we started collecting the data and managing it, manipulating it to fit the types of analysis that we were going to run. So once the database was ready, moving through the analysis, simply just the time, the time that you need to run every analysis.
Oh, okay.
That's why I said we designed the analysis first.
Yes, yes.
We have to think about what we need to do, what the analysis we're going to do, and based on what the analysis is going to do, we start to design the database. Some people sometimes will do something like dummy data to make sure that the analysis that they're suggesting will work. So we'll just get some dummy data or a pilot area, just a small area with all the data defined as we designed, and then run it through the analysis and make sure it works. It might not work. There might be some errors. As you said, right now, when I was before the rest, when I was trying to make this work, I was trying different tools, and while I was trying them on the fly, I haven't made a workflow, but I was trying on the fly, and okay, there's a problem here, there's a problem there. This doesn't work for this, and this doesn't work for that. And sometimes you have to try 1 or 2, 3, 4 tools to
Yes.
reach something that works. And sometimes even when you finish making your analysis model, you find that the model is too cumbersome, is too many steps, and you find yourself asking, can't I somehow streamline this thing? So instead of making it in 10, 20 steps, I can make it in 5. And sometimes you actually find ways to shave the processes and make it very streamlined. So it just takes time, it takes practice, but you do it.
Yes, yes. Thank you.
Yeah. What I'm going to talk about now is a bit theoretical. There is no exercise for that. You might find some tutorials and some of the stuff we're going to talk about. Some people applying some of the tools that we're going to talk about online. But mostly I will going to just be briefly introducing the idea. As we said, our course is a crash course. We're trying to in 15 hours cram as much knowledge about GIS as possible. Not everything that you will get on those 15 hours will be digested in that time. You might need some more time and so on. But this is an idea. So we just giving you an intro to the subject. And as you go more forward into studying GIS systems and technology, you would find that hopefully find that this introduction is useful and will carry you on to more elaborate analysis. So what we're talking right now about is spatial statistics. Now we can consider spatial statistics as a special branch of statistical analysis. It is dependent on we use it as a tool to understand the characterization and characterize the distribution of events across space. Usually it's dependent on the use of software-based tools. It's not something that you can do with a pen and a paper. You have to have some software tools. We have defined methods and techniques to understand the distribution, the pattern, the process, and the relationships that happens inside the spatial domain. It's one of the most important parts of spatial statistics is that it incorporates the idea of space, the proximity, the area, the length, the orientation, the spatial relationships. It incorporates all that inside of its equations, which set it apart from classical statistics. Classical statistics usually steps away from the spatial field and sometimes even puts precaution that the spatial field does not affect it. If we check spatial statistics as a system, just a second, yeah. So application of spatial statistics are numerous. We have it on the physical domain and we have it on socio-economic domain. In the physical domain, you have agriculture, geology, soil science, hydrology, ecology, remote sensing, air quality, and so on. While on the social and economic domain or socio-economic domain, you find spatial econometrics, epidemiology, and disease mapping. We have, as we said, we have multiple users, multiple application, and the field is really, really big and really interconnected. So sometimes you found that an analysis that was used in epidemiology is now used in urban design. Someone somehow read about that analysis and found that it has some relationship to something in the urban domain, and just repurposed the analysis to run in it. You might find something that was done for economical analysis and used also in our field, or used in a different field. Just the fields are really interconnected, and you can take analysis from here and there. Just if there are, I wouldn't say a correlation, but if there are similarities, analogous similarities between the different situations, you find that you can actually move one analysis from one domain to another domain and still works. Spatial statistics depends basically on the first law of geography. The first law of geography was suggested or established by Waldo Tobler. I say established because there are people who are trying to establish the second law of geography, and until now there are debate on what is the second law of geography. There are many suggestions, but the first law is already well established, and many of the theories that we work on today is based on that. And the first law of geography is very simple. Basically, everything is related to everything else, but near things are more related than distant things. So when you consider those points here on the map, the closer the points are to each other, the more related they are. The further they are apart, the less related they are. It's a very simple rule, very simple law, but basically this law defines a lot of the analysis that we do on spatial statistics. It introduces concepts like spatial dependence and spatial autocorrelation, introduces methods like kriging and inverse weighted distance or geographical weighted regression and so on. Those are all tools that are actually dependent on this idea or on this law, which becomes a fundamental law to all spatial analysis. So let's go. We're going to go very quickly through some types of spatial statistics and what they are. So just the main idea. We're not going to go into any equations or something like that, but just the main idea. So, for example, in spatial statistics, we have the measuring of spatial distribution. Spatial distribution is basically the coin, the double coin of the average and the mean and the standard deviation that we have in classical statistics. In classical statistics, we have our sets of data, and we calculate the average, the mean, the standard deviation. We are trying to understand how those, it's a feature pattern analysis. We're trying to understand how things are distributed. And now we have the same measuring spatial distribution. For example, here on the map that we are calculating the population density per square kilometer. And this is the distribution of the population in this map. I think that's California. And you see the red dots are the highest distribution, where it reached 5,000, while the green ones are less than 1,000 inhabitants in the area. And basically, this is what we do. We just calculating the population per square kilometer, and we have the distribution, the average distribution of the population across the map. On another way is to let's use the standard deviation. Using standard deviation, we have an equivalent, which is standard deviation ellipse or standard distance. When we go with the standard deviation or standard deviational ellipse, we have something, for example, like this map. This map is actually about the spread of malaria. So basically, it's the spread of malaria cases between 2007 and 2009, and each of those ellipses represent the standard deviational ellipse of that spread. So we can see how it looked like in 2007, and now how it looks like in 2008, and how it looks like in 2009, and it shows the pattern of how the spread is intensifying and encompassing more area and changing in its direction. So we can use that as well to mark up our data and understand how the distribution is working on the spatial domain. Another part or another thing that we can measure besides spatial distribution is measuring shapes. Now, while working with our data, we'd have to understand that most of the spatial data is based on geometry. It's basically geometry. And understanding the shapes of those geometry, its pattern, its composition, its configuration, is an important analysis tool. So if we look into a map like this, or an image, sorry, and a satellite image like this, and we see the level of compactness of the urban fabric and the irregularity of the different urban plots that we have, or we can actually induce the some form of measure of how well is the urban fabric, how well is that urban fabric, is it well connected, is it is the hygiene in this area good or bad, based on how much compactness, and as a matter of course, due to that compactness, how much airflow and how much sun exposure can the different parcels get. We can also check for the walkability of the area, or for the heat island effects, and so on. So we can study a lot of things, starting from understanding how the fabric looks like. So we have a number of metrics that run on that and understands that. Some other metrics actually understand, for example, there is something called synopsity, where basically we are, this is the road we have, and we are examining how much curvature, or how much how much curvature is it if we take a straight line, and then if we move during in the stream of the actual line, the difference between the two. And as this difference increases, this means that there are many curves and turns in our line. Some people use that in studying transportation networks. Some study it in studying the urban fabric itself, and you'd find many other uses. But in all, you'd find that in measuring shapes, there are some what we call matrix, shape matrix, matrices. Those shape matrices have special softwares. You can run them on GIS, on ArcGIS Pro or QGIS, but some of them actually have their own specific softwares that do run them. And we have those matrices, and you can measure them, take the measurements from them, and use them as indicators for further analysis. So we have something like sinuosity, we have a spatial arrangement, connectivity, diversity, fragmentation, among other matrices. Another thing we study is the spatial autocorrelation. Now, as we said, that the spatial autocorrelation is actually spatial autocorrelation and spatial dependence is one of the major factors that makes the difference between classical statistics and spatial statistics. We want to measure the spatial autocorrelation. We want to measure the spatial dependence. When I check the spatial autocorrelation, I'm basically checking, is there clustering in my data? Is some form of characteristics to the pattern exists or doesn't exist? So do I have the data in clusters? Do I have my patterns in clusters, notable clusters that I can see? or it's just dispersed all over, or just dispersed, and even dispersion has its own rules. So clustering has rules, dispersion has rules, and then we have the in-between, the randomness that we can talk about. So are we going to measure that? And we have several tools. We have average nearest neighborhood. We have something like Global Moran's Index, which actually just simply measures if there is clustering in our data. If there's clustering, we get a positive figure. If there's no clustering, we get a negative figure. And if there's zero, we just say that there is no. No, sorry. If there are clustering, we get a positive figure. If it's dispersed, we get a negative figure. And if there is no clustering, we just get a zero. So the no clustering is the in-between. Do you understand this point? Clustering, dispersed, and the no clustering.
Yes.
Okay. Another way to understand the spatial autocorrelation is using something like the Gettys-Ord analysis or Enslin local Morans. Those don't check if there is clustering, they check where is the clustering. So it's not just I'm checking. Yeah, if you run a global Moran's eye, you end up with the index. Just an index, a number, you get a number. But if you run the Gettys-Ord or Enslin local Morans, what you get is a map where you actually show the clusters at hotspots, and sometimes hotspots and cold spots. In all the running of any spatial autocorrelation tool, there is something called the null hypothesis, and the null hypothesis is basically there is no spatial autocorrelation. So the null hypothesis starts from when you run any analysis of those three. The null hypothesis for them is that there is no spatial autocorrelation. This is what we are going to look for, and we actually call that complete spatial randomness. So this is complete spatial randomness. If we don't get that, if the null hypothesis is unproven, then this means that there is some form of rules that govern the pattern to create the clusters or to create the dispersed pattern that we see in reality. And then we can move forward after that to study why the patterns show like this. For example, this is a quick example about using the Gettys-Ord tool to check the clustering of the 911 calls. So they have all the data for 911 calls, and they are pooling the high volume to get the hotspots and the low volume to get what is known as the cold spot. Now, if we run it without any normalization, just the numbers of the 911 call, we would get some form of a biased data. So just imagine this: you're running the 911 call for the entire city, emergency call for the entire city, and you have some districts that has very high 911 call, while other districts have very low. And then you check them and you find, okay, one of those districts is actually highly populated, very congested, has a lot of different commercial and so on activities, while others are remote suburbs on the edge of the city. So, of course, there will be some form of bias. But if we normalize by the population, if we normalize the calls by the population and look at the hotspots and the cold spots that we get, now this data, the map that we are shown, is a map basically after being normalized by the population. So when we get high value or hot zones, high volume of emergency calls in a place, we can't come back and say, oh, this high volume is because there is high levels of population here. No, we already accounted for the population. So we can check now, why do we have high percentage of emergency calls in this area? Is there a problem in its design? Is the problem in its activities? What's the problem that causes high emergency volume calls in that area? And it allows us to make a more proper study. So this is one example, quick example of using a GIS or the study. Another thing that you use is also measuring spatial association, which basically means that we are doing regression. So spatial association, we're looking for regression. Now, statistical regression or classical statistical regression, you have linear regression, binomial regression, logistic regression, and so on. So we are going also to have some of our own tools to run regression analysis. We have some tools. We have something like the spatial filtering. We have economic spatial regression. We have geographically weighted regression. I think geographically weighted regression, you'd find a lot of literature on it. It's quite prolific as a regression tool to be used with the spatial analysis. We, of course, running that, you'd find that those tools account very much to spatial autocorrelation and to regional variation. And this is where we have a great difference from classical statistical tools. Classical statistical tools, when running regression, will deliberately compensate for spatial autocorrelation. And you'd find that in many statistical papers and statistical textbooks, when they are explaining classical statistics, they always tell you when you're dealing with data that have some form of a spatial component or geospatial component, you find this always that comes to the surface. How are you going to deal with spatial autocorrelation? How are you going to compensate for it or eliminate it or mitigate its effects? In working spatial statistics, we're not trying to mitigate its effects. We're trying to measure it and account for it in our equations. It's one of the fundamental aspects to spatial statistics. Another thing we can use spatial statistics for is modeling surfaces. When modeling surfaces, we go into the field of spatial statistics known as geostatistics. In ArcGIS Pro, you'd find that there is actually a toolbox, an entire separate toolbox called geostatistics, and it has to do with that, modeling surfaces. It has several tools. It runs on extrapolating data and doing prediction, error, and probability surfaces. So for the examples that we have here, those are 3 different maps. One of them is terrain. So basically, this is a height map. Each pixel or each cell in this raster corresponds to an elevation. On the other one, this is rainfall, and so each cell here basically corresponds to precipitation. And this is population, so each cell actually corresponds to a number of population in this cell. Usually, you don't get the data in this format. What you get is usually point data. We have some points, we have elevation in some points, we have measurements on some points on the amount of rainfall in certain measuring stations. You have measurements on the population across entire zones, not across each square meter of the city or something like that. And we have to extrapolate the data to the entire map. So in each case, we have to extrapolate the data to the entire map. From one point, from several points across the map, I have to extrapolate what's missing in between. Of course, as accurate as the data, as the points we have, is the accurate the data we get. Some of the tools that we use in geostatistics is kriging and variograms. You can find both of them in ArcGIS Pro, and you can check them more if you'd like. But this is basically the fields that we go through. So those are the fields of spatial statistics that we go through. So the question that comes to mind sometimes is, why do we use spatial statistics? I'm not sure if you've heard of this book before. There is a book called How to Lie with Statistics. It's a small book, but it's really, really very insightful about misuse, the use and misuse of statistical data. Have any of you heard of that book before? Have any of you read it before?
No.
Well, I suggest you have a look at it, How to Lie with the Statistics. It's really insightful, and it gives you a wider perspective about how just small manipulation of data could actually cause us to present an image that is far from the truth. Working with spatial statistics actually aims to represent our data in the most relevant way possible. We get new data every day, and we are going to try to represent it. We're going to have to make some visualization, and we're going to check that visualizations ourselves, and we're going to offer these visualizations to others around us, our clients, our colleagues, and so on. Our visualizations, if based basically on our whim, based on subjective factors rather than objective factors, will actually induce what we're talking about, lying with data. We have the data, but we're lying because we are not showing the most relevant, or as we say here, the most statistically significant data. We are not showing the most statistically significant data in our visualization. We are showing irrelevant data, we are showing marginalized data or outlier data because we like it, or because it makes for a better visualization, or because we're outright lying. But there might be many reasons, but at the end, the end point is the same. We make visualizations that are not worth much and convey wrong messages. But if we can actually always check our data, when we get data, new data, and we check the data and we find ourselves talking about, okay, this is, we're checking the data we have, and this is the statistically significant data that we have, and we highlight that data in our visualization, we can actually take more concrete action and be truthful to ourselves and to our clients. One of the most important tools out there for doing just that is Geoda. While you can do a lot of data exploration using ArcGIS and QGIS, Geoda is actually a software that is, it's an open source software, so you can get it anytime you like. And it's completely designed to explore for statistical exploration. So you get your data, you enter it onto the system, and you start exploring the different types of data. You start running different types of statistical tests. You gather this data, you gather the visualization that comes from it, and you get a better understanding for the entire system. I think I have a short video for it. You can just check.
Are you looking for an easy way to analyze your geospatial area data? Would you like to gain insights faster than you usually do? We developed a software called Geoda that introduces people to the analysis of spatial area data and helps you gain a quick overview of it, find interesting patterns, and test hypotheses. Geoda provides a user-friendly and graphical interface to methods of...
Did you hear the sound, or the sound was not working?
We heard the sound.
The sound was okay,
Yes,
but the video was not playing, or was it just a photo?
2 slides, maybe.
No, it's just they are talking and moving. It's not really a video. It's slides, and they're talking about it. So,
Are you looking for an easy way to analyze your geospatial area data? Would you like to gain insights faster than you usually do? We developed a software called Geoda that introduces people to the analysis of spatial area data and helps you gain a quick overview of it, find interesting patterns, and test hypotheses. Geoda provides a user-friendly and graphical interface to methods of exploratory spatial data analysis, also known as ESDA, such as spatial autocorrelation statistics for aggregate data and basic spatial regression analysis for point and polygon data. You can explore statistical and mapping views of spatial data through linking and brushing to discover correlations, clusters, and trends, and to detect unusual observations. Geoda supplements other GIS programs like QGIS or ArcGIS by focusing on specialized spatial analysis functionality. It is free for non-commercial use because it was funded by federal agencies like the National Science Foundation and the National Institutes of Health. It is cross-platform and runs on Windows, Mac, and Linux, and it is open source. The Geoda library is currently under development, so you can use it in Python, R, Postgres, and other programming languages. You can also use Geoda in many languages. Volunteers have translated the English version of Geoda into Chinese, Spanish, and Russian, and continue to work on other languages. To contribute, please see the description of this video for more information. So who mostly uses Geoda? As of September 2020, over 360,000 people have used the software since it was launched in 2004. And this includes not just faculty, researchers, and students in academia, but also government organizations and nonprofits across the world. So how do you start? First, you can import, convert, and export data in different formats. Then, you can also transfer variables and create new ones, and also display additional layers. But why use Geoda? Our software allows you to gain new insights from your spatial data by interactively exploring the data in multiple views with a user-friendly interface. You can detect patterns and correlations, find trends with different maps and statistical views, and detect outliers like here across box plots and box maps. We've recently introduced a lot of new cluster functionality in Geoda 1.16, as well as many global and local spatial autocorrelation statistics. After exploring the spatial data in multiple views and generating hypotheses about relationships, you can produce these global and local spatial autocorrelation statistics as well as spatial regression models. You can download Geoda by following this link. New versions of the program are released regularly. Additionally, you can access Geoda-related resources on this webpage. Luke Anseling, who founded Geoda and directs the University of Chicago's Center for Spatial Data Science, has created extensive tutorials for all spatial methods and tools in Geoda, which you can access for free on our website under the documentation section. Also, if you have trouble finding the Geoda tool you need, we have developed a cheat sheet that can help you find your way. Finally, we have a YouTube channel with lots of recorded lectures of Dr. Anseling explaining the spatial methods implemented in Geoda and examples of how to use it. If you would like to get in touch with us, you can also find our contact information in the description of this video or submit a ticket on Geoda's GitHub site. Enjoy!
So, as I said, this is a tool that should be helpful in spatial statistics exploration. So you can use it to explore the data, produce all the relevant statistical analysis that you need before moving on to more rigorous spatial analysis of your data, more designed spatial techniques and spatial design techniques to use.
Sorry, I have a question.
Yeah.
For example, if we have a model on ArcGIS Pro, so we can import it or in Geoda, or
yeah, I can get many
does
formats.
it eliminate the
Geoda.
functions or the analysis that is made in ArcGIS Pro, or it's another tool? You know, it's an extension, or
No, it's not an extension. It's a standalone
separate
program.
tool. Yeah.
It's a standalone program.
Standalone program.
Yes.
And they are not linked
No.
in a
A
way.
standalone program, and you can get it. It has its own tutorial. You can get to the website and you find the documentation section. They have a very extensive YouTube channel with short videos, nothing very long, but short, concise videos. So you can start with them. The first interface, how to load data. You can load different formats. How do you do that? What do they need when you enter the data? And then how to start doing this statistical exploration tests and so on.
Okay, it's another tool for analysis, for example.
Yes,
Yeah,
it's a total tool. Yeah, it's another tool for analysis, but this is what it is. It's a tool for analysis.
a tool for analysis. While
Just that.
ArcGIS Pro, we can
ArcGIS is a
make
more
data.
general purpose tool. You can do design work on it.
Yeah.
You don't only stop at analysis. You can do more work on it. Geoda will help you if you want to test the data. The idea of looking for the statistically significant relevant data and so on. This depends on running certain tests on your data. So Geoda will help you with that. They have all the tests. They are already standardized and categorized, and you find them into special menus, and you have this cheat sheet that they have where you actually tell you why do you want to test the data, for what exactly do you want to test the data, and if you want to test it for that or that or that, use this those tools and so on, and you move from there. So that's why we can consider it as a very an important tool for exploring the data.
Just one more quick question.
Yeah.
When you do it in Geodata, for example, can you then re-import it in ArcGIS Pro to continue, or it's limited to that?
Importing data from, you can import some data from it, but not everything. But you can already get the data as I mean, they already produced you the maps and the images that you can see, and you can use it in further in your analysis. And you already know, after the exploration is done, you already know where is the significant points in your data, so that when you continue in ArcGIS Pro or continue in QGIS or in MapInfo or any other software, you know what to look for and what to take care of.
Yeah, thank you, noted. Thank you.
Okay, I'm going to, this is a bit of a long, the next slides, but I'm going to move forward in it quite fast. There is a number of videos, but we're not going to check them. We're going to just go fast through them. The idea is to represent spatial analysis tool sets. Those are a collection of programs that has to do with spatial analysis at one level or the other. Some of them are very small that you have to run the scale of a room or a building, and some on the scale of a street, and some would allow you to just run whatever analysis you want to run on the scale of the globe, if you wish, if you have the software or if you have the hardware capacity and the data. But anyway, so this is basically a collection that I've made, and I've categorized it, so it's my own categorization. So let's go through it fast and check what we're talking about. So first we have what I call general purpose tools. So we have, of course, ArcGIS Pro. We have been talking about it for the last 2 days and today, and I consider it a general purpose tool. We can use it for many things, whether it's spatial analysis or mapping or visualization or field work or going into designing and geodesign and so on. So we can use it on different levels and different scales. Comparable to that, we get something like QGIS, which is an open source program and have quite a following and has its own merits and quite accessible software. Beside that, we have some other softwares like MapInfo, Maptitude, Mapbox, even Google Earth, like Google Maps API and Google Earth Pro, where we can actually use some developer tools and build our own applications if we want to. So we have some general purpose tools that might not have the entire functionality of something like ArcGIS Pro or QGIS, but still offers some applications. Others of general purpose tools, I place statistical tools as well with us. Sometimes we will take some of our data and run it through pure statistical tools and then continue working in GIS, and sometimes we'll do the reverse produce the data from GIS and go take it to statistical softwares. Right now, many of the GIS platforms are offering more and more statistical tools and more sophisticated statistical tools, but sometimes you find certain functions that you want to run that actually doesn't exist within the some analysis that you want to run that doesn't exist within the library of tools inside the GIS platforms. And the only way to do it is to take the data to a pure software and run them through it. One of the most famous, of course, is the SPSS software. Of course, you have to buy a license for that. Another one, which is somehow comparable to SPSS, is PSPP. Now, that's an open source program, so you can download it easily and directly work from it. It has similar interface to SPSS and runs many of the same functions that SPSS does. So basically, I look at it as an alternative, which is open source and gives us a lot of capabilities that we can use. Another one of the general purpose tools is also for statistical analysis is SAS, which also allows us to build our own dashboards with the different data and visualization for it. Not specially, of course, but we can put the graphs and the reporting and the tables in it easily. Besides general purpose tools, we move into specialized tools. So for one, we have the remote sensing tools. Here we have a program like GIS Imagine. It has existed for a long time and would allow you to run analysis for remote sensing data from satellites, from drones, from aerial surveys, and so on. But it only works on that. So only works with spatial data, with remote sensing data. We enter raw images, we manipulate the different bands, we combine them and recombine them, and then run through several analysis of the data, several analysis of the remote sensing data. But we won't do anything more. So if I want to go to work on GIS, I have to take whatever the results I get from a remote sensing platform and then move to another platform for GIS and so on. Another software that has to do with remote sensing is ENVI. ENVI is also a comparable software to GIS Imagine and has many of its capabilities. So they are basically two comparable softwares. You have GIS Imagine and you have ENVI, and you can work with that or that. And as I said, they will only deal with remote sensing data. Once you're finished, once you have your data ready, basically you're doing the processing for these images before moving them to ArcGIS and work with it. Right now, ArcGIS Pro has its imagery feature. You have a ribbon that deals with imagery, and it does a lot of remote sensing functions. But of course, those specialized programs have much more capabilities than ArcGIS itself. Another applications that we can get are urban applications. This is one of the it's becoming one of the most famous applications that we have now, which is ArcGIS City Engine. If you have an ArcGIS Pro Advanced license, usually you might get with it an ArcGIS City Engine license as well. They might work for both. And ArcGIS City license basically allow us to build the city using what we call procedural city generation. Basically, we set the rules by which the city should be built, by which the roads should be laid out on the land, and how the parcels, the minimum size of the parcels, the maximum size of parcels, the proportions of its dimensions, what is how do we deal with the central area of the city, how do we deal with the fringes, how do we deal with the suburbs, the building heights, the building styles, everything. We can actually enter into the rules, all our guidelines for building the city. And once we're done, we have 3D of the city all generated for us through the system, and then we can start running different analysis either through City Engine or either through different program suites. We can take that into other programs and run more analysis. And of course, we can not just listening to me, you might think, okay, we're building or we're designing a new city, but you can actually do the same to build an existing city. So you can build on the system an existing city and run your calculations and your analysis on it. Maybe you have we can check one of the videos. So we have a video for ArcGIS City Engine. As you see in the video, we can this city block, we have it, we can change what we want. The city is drawn with its own roofing and facades of the building. All of that is something that we designed. And you see when the one who's editing made that new street, directly after making the street, the system generated the buildings inside that block, and with own the facades and the color schemes and so on. Everything was already programmed, and so it was done automatically. And then we can, of course, go on and change what we want individually per building or per block if we wish. Another software that can work in tandem with City Engine is actually ArcGIS Urban. ArcGIS Urban is a web-based application. So basically, we have to do our work on City Engine or any other the software that actually allows us to build the city in 3D and then take that into ArcGIS Urban and run some of specialized analysis that are done to analyze the urban fabric.
Cities today face major.
Another software we have is also CityCAD. CityCAD does not go into the level of softwares like City Engine, but it allows us to draft an entire 3D city with all the trimmings, with all the elements that we might have seen or seen a facsimile of in ArcGIS City Engine, but we also have to design it bit by bit. I mean, City Engine is more procedural oriented, which makes it much easier to build an entire city inside of it. Okay, I'm moving fast between one to the other because there is a number of videos here. So not every video will work. Okay, another tier of programs that we have are environmental application program. Those are programs that are directed to running environmental analysis, whether on an urban scale or on a building scale. One of the most famous is EnviMet. EnviMet allows us to run 3D urban climatic modeling. We can run it around the buildings. We can manipulate the microclimate of small urban areas and adjust our designs based on the results of the analysis that we get.
The urban environment is a mosaic of adjacent forms and surfaces with a unique spatial morphology that gives rise to distinct meteorological conditions. The urban climate and its study are becoming increasingly important as these regions show significantly higher rates of population growth and development, which will exacerbate the environmental challenges that are already present. Driven by the desire to understand and simulate the environment as a holistic organism, EnviMet, a microclimate simulation software, was developed based on objective scientific methods so that the effects of proposed architectural and planning solutions are measurable. EnviMet is a holistic three-dimensional model used to simulate complex urban environments and to assess the effects of green architecture visions. It is designed for a wide range of temporal and spatial inquiries and can reveal credible differences in urban geometry by capturing their impacts on microclimatic conditions. EnviMet includes the capacity to analyze a wide array of spatial scales, from systems as small as a courtyard to as large as an entire city, depending upon the goals of the project. To create sustainable and resilient living conditions, this software will help to minimize heat stress, air pollution, and wind risk by providing up-to-date numerical simulation techniques to elucidate the impacts of our architecture and planning proposals on the urban fabric in a fashion that goes beyond intuition and assumption. There is an endless variety of building and ground plane material options made available through the ability to specify parameters such as thickness, albedo, specific heat, density, and many other factors. The software also enables the calculation of wind dynamics in complex urban settings to illustrate the fluvial impacts of different urban design decisions, which can be used to inform ventilation or pollution dispersion. In order to integrate EnviMet into existing workflows of industry professionals, recent updates open a new chapter in how users can construct models and simulate data. Moving away from grid-by-grid editing, Monde enables vector-based approaches that make it easier to generate models or to change spatial resolution with just one click. Users can import existing vector data, such as CAD and GIS shapefiles, in addition to accessing the worldwide database of OpenStreetMap and OpenTopography to create EnviMet models. With the application of vegetated infrastructure on roofs and walls becoming an important tool in green building design and urban planning, EnviMet's new green wall module enables the user to accurately simulate the complex interaction of vegetation, substrate layers, and fixation materials mounted on facades or roofs. In order to produce valid results, the modules take into account a multitude of parameters, including the opening and closing of stomata based on the validated plant model and the effects of multiple reflections and local infrared radiation. With Albero, the user can simulate complex three-dimensional plants and manage both their properties and appearance. This also enables the creation of new plants to emulate specific species of interest, accounting for features such as root shape, canopy size, leaf area index, leaf albedo, and the ability to distinguish between evergreen and deciduous species. The new EnviMet plugin for Rhino Grasshopper has been developed in the Ladybug tools. This plugin enables users to convert Rhino 3D designs to EnviMet model areas and run simulations without even opening the EnviMet software suite. Since our users are typically already experts in their core applications, this makes it easier and faster for professionals to adopt these tools. In order to mitigate the impacts of climate change and population growth, it is important that we no longer operate using trial and error, but instead be more critical of site performance. A more holistic approach can resolve the dynamic interactions between plants, buildings, and the atmosphere to quantify site-specific environmental performance metrics. The future of architecture and planning is here. It is time to elevate the design process to a new level.
So that was a bit of a long video, but this was NVMet. Another program that is similar is Design Builder. Design Builder is more focused on the building itself, so it doesn't do urban analysis, but it does its own environmental analysis inside the building, and it has several modules that work at several features of the environmental analysis, whether it's temperature and humidity, or HVAC, or solar radiation, and so on. We have, beside those, we have something like special toolboxes and application. Those are some applications that sometimes they are very specific, they are small factor, and some of them are not standalone, but actually plugins that work with other programs. You get those from time to time. You would find them, and you find this like this. It's very specifically oriented towards a certain type of analysis, maybe even running one or two equations, and it doesn't have a lot of options for us. One of those tools is, for example, the FragStat. FragStat is an application that works with landscape metrics. As I was talking previously, when I was talking about the shape metrics as one of the things that spatial statistics measure. One of those is actually called fragmentation metrics, landscape metrics and fragmentation metrics. And FragStat is a standalone program that actually does that. You download the program and you can run certain matrices across your data and get the indices and the matrices for it. Another one, this is not standalone, this is more of a this is a plugin, is Batch Analyst. This used to work with ArcMap. I'm not sure if we can still work that in ArcPro, but this was a standalone a plugin tool that we added to the toolbox, and it allows us to do one of those batch analysis is one of the analysis that is done into shape metrics. So it's one of the shape metrics that we use. Another tool is Esri GIS. Esri is a software that is basically designed for analytics of spatial statistics, special ones like logistic regression on the spatial plane and so on. And okay, this is one of them. Another special tool is Space Syntax. Space Syntax is a special program that deals with the connectivity of linear elements on the urban environment, and how you use that to evaluate the connectivity of urban spaces, of different urban spaces. It's dependent on drawing the axial lines of all the streets and roads in a given neighborhood or a given city, and then evaluating them with ranks based on a specific theory. And it can give you the idea, give you the evaluation for that street network. When you get the slides, you can check the websites for it, because if you make search for Space Syntax, there are two websites, and one of them just takes you to a company or something like that. This is the actual Space Syntax website. So when you get the slides, you can check the website and see their offerings and papers on the use of their program and so on. Of course, Grasshopper is very known plugin for the Rhino software, and the importance of Grasshopper is not just that it helps with the procedural programming for the system in Rhino, but it's the idea that we can couple it with other softwares, especially something like the Ladybug tools, which offers us a great variety of environmental analysis tools on several levels, whether we're talking about the Ladybug or the butterfly or dragonfly or honeybee. There are many. Those are some of the plugins the Ladybug plugins that works with Grasshopper, but there are other plugins outside that also go with Grasshopper and also offer a great variety of work. Of course, if we're going to talk about DEMS, then we can't forget about Rhino and Revit and SketchUp. Rhino, of course, for working with Grasshopper, that's the only way. And Revit and SketchUp, while allowing you to draw 3D visualizations of your designs, whether it's for one building or for a neighborhood. Maybe a city is pushing it too much, but the visualization you're drawing has more info, especially in Revit, where you can actually add your BIM data, and this would allow you to move another step. There is a software now, an online application called GeoBIM, which is a collaboration between Esri and Autodesk that actually combines the fields of GIS and BIM together in work. So it could be an interesting approach if you're interested in that. Beside the special toolboxes, we get to programming languages. We're working with GIS or spatial analysis in general. At some point, you will touch on programming. You don't have to be a programmer. You don't have to be a developer level, have developer level knowledge. You can only have beginner level knowledge, and it's enough. If you want more, you can train and take more courses and so on in them. One of the most important software that is now programming language that is now used in many special analysis softwares is the Python. Python is a straightforward language. It's simple, it's easy to understand and easy to learn. And everything in Python is divided into libraries. So whatever you want to do, just basically load the library. That's what we say, load the library and start working from them. And some of the most important libraries that we have that has to do with GIS is TensorFlow, PyTorch, and GeoPandas. GeoPandas, from the name, has many functions that work with GIS analysis, while PyTorch and TensorFlow are actually two libraries that work with machine learning and deep learning. So if you want to work with AI and develop AI tools or do AI analysis, at one point you might find yourself doing some coding on TensorFlow or PyTorch. Another programming language, and I'm putting both of them together to make it easier, is the Rust and the R. They look similar, but Rust is actually a programming language similar to Python, although not as simple. While R is actually is called R Project for Statistical Computing. It's a tool for statistical analysis, runs as a programming language, so you have to write in coding, write your data in coding, and it gives you the capability of either giving you reports or giving you graphs or visualizations to your own statistical analysis, and it can be coupled in different ways to ArcGIS and other GIS platforms. So that's it for this. Just to finalize, I have a couple of tutorials that has to do with what we went through today that I think would be beneficial for you to have. So one of them is getting started with spatial analysis. I'm going to just add the link to the chat. So this is a simple exercise about using different tools of spatial analysis. And another tool here about using story maps. And this, I don't think you did any dashboards. Maybe you've seen it, but you haven't done any dashboards. So those are two tutorials, 20 minutes and 30 minutes, about how to work with dashboards and how to create your own dashboard. It's considerable now, a considerably important tool while working with different GIS applications. When you deal with your clients and you have to share something, sharing a dashboard is very effective tool. So that's it for me. I am done. And if you have any questions.
Do we have any questions?
Thank you so much for your effort.
Thank you for all the lectures.
You are welcome.
Yes, I would like to thank you for this workshop and your effort, and I am asking for what is your advice for us, because I guess almost all of us it's our first time to be introduced to this system and all these softwares. So what is your advice to proceed in this process? So, do we have still watch more tutorials, or decide which how to decide? Also, another question: how to decide what is beneficial for us in each sorry in each speciality? Yeah, I don't know if you get my question. So
well, I do get your question. First of all, hands-on training. So you need to train more, try the exercises. If you've done it once, do it again. You're just training. This is the first time you get exposed to something like this. So doing the training again is helpful. Many of us did that when we learned the program the first time. So that could be very helpful, as well as check the sites for Esri Academy and Learn ArcGIS. Both sites I have shared with you before. Those sites are very useful. You get something, for example, right now, ArcGIS Academy, Esri Academy. Esri Academy is running a number of MOOCs. I think MOOC is massive online
open course.
Something course. Yeah. They are very useful in teaching you how to use certain aspects of GIS. And Esri is very thoughtful in designing their MOOCs. So you get the MOOC that is basically usually 6 weeks. The MOOC is 6 weeks. They expect you to work for 1 day a week. So 1 day a week, they open usually Wednesday or something like that. They open the tutorials, and it's open for basically each week. They open a new tutorial, a new exercise. There is some videos for explanation, and you have the exercise to go through and some quizzes at the end. So it's something all in all between 3 to 6 hours per week. And while the MOOC covers a broad topic, each of the exercises in each week takes a different perspective or a different aspect of that point. So it's a very good introduction to many of the topics in ArcGIS and many of the tools that are present in ArcGIS Pro. And basically, it's a very good tool for us to learn from. So my advice is always find whatever courses they have, whatever MOOCs they have, register to it, and start learning from them. Another thing, find someone involved into ArcGIS analysis. You have to have experience. I mean, training is good and all, but you have to use that knowledge in some form of either professional capacity or in some form of research project. You have to use it beyond the exercise limitation. So once you do that, it gives you a lot of pointers about how to proceed from there. As for how it affects your own interests, I mean, everyone knows his interest, and you can start to see how you can how GIS can apply to that interest. You can search for books and papers, how it is used, the different applications that it was used in, and see if you want to learn more about that. You start searching for tutorials first in Esri Academy and LearnGIS, and then on the internet or on the forums, the Esri forum, you can check many resources on it as well. So it's way where you can start developing your skills.
I have to thank Abdulmanam so much for this informative 3 days and for giving us your time to give us some hands-on practice on how to use GIS for beginners, to say. And I might have a question for for our attendees. If you have any feedback, any comments on how to make this course better, or something you like, something you didn't like, you are free to tell us, because if we hear your negative feedback, we can just build on that, how to make things better the next time. And also your positive feedbacks are most welcome, so we can enhance ourselves. So please let us know your feedback. We would appreciate it.
I think we needed to practice more while taking information in the same time. Maybe we can, instead of 3 days of lecture, we can make it like 5 days or 1 week, and make the 1 hour after the break time is for practicing while taking the information at the same time.
Good to know. What else?
I actually have a positive feedback about as a beginner in GIS, listening to the lectures, some things might seem alien, but once we go to the tutorials, it's like we're remembering everything you have said, and it makes more sense when we're applying that step to step. So for me personally, that was a very smooth process.
Thank you so much, Eva. I think Dania's feedback is not negative, however, because I have already discussed that last time with Monaim, and we went through it that due to the limited time that he wanted to give you more insights about the capabilities of ArcGIS and how can we use it and so on, giving you the theory background and giving you trainings, and also that it's online, it's not a physical workshop. That's one of the how we say that the drawbacks that we have, that it's only online. So if we are sitting all together in just one room, so we could have done more things in this regard, Dunya, that you can have the hands-on practice directly after what Monaim was explaining, and working all of us on the same database and so on, so we can see that. However, yeah, your comment is definitely in order. Do you have any things that you need to share with us?